Finding the energy released from a nuclear decay and the kinetic energy of daughter products. A worked problem using conservation of energy and momentum for AP Physics 2. The problem you can't read, but it's basically we're taking radon and changing it to polarium and helium, and we want to find what energy is released and then the kinetic energy of the daughter products. So I've got the nuclear reaction written down up above, where you can read it now. And now we're going to start analyzing bits and pieces. So the easiest bit is looking at the energy released due to mass conversion to energy. On the radon side, we have 210.9906 units. And then on the product side for polonium, we have 286.9816 units. And for the helium, or alpha particle, we have 4.0026 units. So we add the product together, and we have 210.9842, and we look at the difference between the two masses. And we have loss mass of 0.0064 units. This is the amount of mass that has been converted to energy from the original radon reactant. And this has been converted to energy thanks to Einstein's E equals mc squared equation. What we're going to do now is change the units of mass into an energy unit. We have 1 unit of mass, 1 U, is equal to 931 MeVs over c squared. So we have 0.0064 U's times 931 MeVs over c squared per U times c squared. So we get the energy released was 5.984 mega electron volts. This number, 931 mega electron volts per c squared, is from the AP Physics 2 equation sheet. Alas, I got the problem from my WebAssign account, and the WebAssign account I use, the particular book that I'm using it from, uses 931.5 mega electron volts per c squared. So even though that's not the AP equation sheet number, I'm going to use the one from the WebAssign, so my numbers all agree, so I can double check my work too. So the actual energy released using that number is 5.9616 MeVs. So that was the easy part. Now we go to the fun thing of finding the kinetic energy. So what is the kinetic energy of the alpha particle? And we're going to start with the alpha particle because it's smallest and easiest. We're going to use conservation of momentum and conservation of energy to solve this. Conservation momentum is the momentum before is equal to the momentum afterwards. So the momentum of the radon in the beginning is equal to the momentum of the polonium and alpha particle at the end. But the radon was sitting still at the beginning. So the original momentum of the radon is 0, mass times velocity, and that's equal to the mass of the PO times the velocity of the PO plus the mass of the alpha particle times the velocity of the alpha particle. Conservation of energy tells us that the energy released is then utilized by these two daughter products as kinetic energy. It's not stored. It was stored before it was a binding energy. Now it's being released as kinetic energy. So the released energy, Q, that we solved for in part A, is equal to the energy before, if you would, and then that's equal to the kinetic energy of the two daughter products. We have two unknowns, the velocity of the alpha particle and the velocity of the polonium particle. And we have two equations. So now we can do some clever substitution. We're going to solve the first equation, the momentum equation, for the velocity of the PO. So I'm rearranging the equation for velocity of PO using the magic of algebra. So I have the velocity of the polonium solved in terms of masses and velocity of alpha. Now I'm going to go back up to my conservation of energy equation and rewrite it using the equations for kinetic energy. So Q equals 1/2 mPO V PO squared plus 1/2 m alpha V alpha squared. Now I'm going to take that velocity of PO and substitute it in right there. Rewriting this equation, which looks messy, but really the algebra is very simple. Q equals 1/2 MPO times the quantity M alpha V alpha over MPO, and that's a negative number, squared, so the negative is going to disappear, plus 1/2 M alpha V alpha squared. So I've just substituted in. A lot of variables, but it's just simple substitution. I've rewritten it up at the top, and now we're going to do some more stuff. So I'm going to rearrange my terms a little bit. I'm just trying to be clever about all of this. Actually, I'm deliberately being clever. So I'm just rearranging some stuff in my first term, and I'm canceling some things because I've got an MPO squared in the bottom and MPO not squared on the top. And now I'm going to rearrange that first term a little bit more. I'm pulling out the M alpha and the MPO, and then I have left 1/2 M alpha V alpha squared, plus, of course, the second term that I didn't have to do anything with. But realize this 1/2 M alpha V alpha squared is just the kinetic energy of the alpha particle. And so I now can rewrite those two things as kinetic energy of the alpha particle, which is what I'm trying to find. Now I'm going from a very complex many-variabled equation to something a little bit simpler. I have the mass of the alpha divided by the mass of the PO times the kinetic energy of the alpha plus the kinetic energy of the alpha. Pulling the kinetic energy of the alpha out, thanks to the distributive property of multiplication, I get kinetic energy of the alpha times the mass of the alpha divided by the mass of PO plus 1. Well, I know the mass of alpha. I know the mass of PO. I know how much energy was released. So I can now find the kinetic energy of the alpha particle. So I'm going to plug in my numbers, finally getting away from all those variables. And I get 5.9616 divided by the quantity, 4.0026 divided by 206.9816 plus 1. End of quantity. Be very careful entering it into your calculator. Be sure and use parentheses. Watch out for order of operations. You do it all correctly, and you should get the kinetic energy of the alpha particle is equal to 5.8485 mega electron volts. Voila. The last question, what is the kinetic energy of PO, is actually very simple now after doing all that other work in part B. We know what Q is, we know what KE alpha is, and Q is equal to KE alpha plus KE PO. So now we just plug in some numbers and we get an answer. So 5.9616 equals 5.8485 plus KE of PO, and KE of PO is equal to 0.1131 mega electron volts. Thanks to the magic of algebra and conservation laws, this actually isn't that hard of a problem. A little messy, but really not too tough. Have a great day. Thank you for your time.